Good evening, everyone. Welcome to the week 8 live interaction session for the course Fabrication Techniques for MEMS-based sensors from the clinical perspective. I'm the course TA, Rayan Jesma. This is about me. And every week on Monday from 6 p.m. to 8 p.m., we'll be having the weekly live interaction session where we will discuss the doubts or like problems regarding the content that is covered in the corresponding week. So this is my meeting link, and this is the YouTube channel where the recorded videos are uploaded, and in the Google Drive the slides are uploaded for the content. If you have any doubts, you can reach me at rayanrjesma@gmail.com. Okay. A quick recap regarding what was covered in week 8. In week 8, we had content regarding the microchip for rapid drug screening and also a microfluidic chip for rapid bacterial antibiotic susceptibility testing. In the case of the rapid drug screening, what we were looking into was like the drug screening for cancer cells. So now let us move on to the problem question. A quick recap. So in week 8, what so a quick recap. In week 8, the content that was covered was a microchip for rapid drug screening and a microfluidic chip for rapid bacterial antibiotic susceptibility testing. So in the case of rapid drug screening, we were looking into the drug screening for treating cancer. Okay. So now let us move on to the problem section. In problem 1, the question is what is the purpose of the heater in drug screening device? Option A, at elevated temperature, sensitivity increases. Option B, to maintain normal human body temperature on the chip. Option C, matrigel is stable only at elevated temperatures, that is 320 Kelvin. Option D, all of these. So which one is the correct answer? So we know that heater is generally used in order to increase the temperature. Alright. In one of the previous lectures, we saw that like we used the heater for increasing the temperature, so because the sensitivity at higher temperature was higher. But in this case, why do we use the heater in the drug screening microfluidic device? Okay, so the important thing about like having microfluidic devices for drug screening is that we want to reduce the time uh, compared to the conventional methods, like by administering instead of administering the drug directly to the patient and see whether the drug is working or not. We want to like do a trial and error approach using a system which is like closely which mimics the behavior of a human system. So one important thing is that our human body temperature is around 37 degrees centigrade. So if we are testing a drug, we also need to mimic the temperature of the human body. So for that purpose, we are using a heater in a drug screening device. So the correct answer is option B. And also, let's say how the drug reacts with the like various cells will also can also vary depending on the temperature. So to obtain a realistic scenario, we need to have the realistic conditions, like conditions that are same as in vivo. So we need to maintain the temperature of a human body on a chip. So the correct answer is option B. Is this clear? Okay, so now let's move on to the next question. Problem 2. In vivo situation of our body can be mimicked most faithfully by option A, microfluidic chips, option B, IDE structure, option C, microtubules with peristaltic pump, option D, all of these individually can mimic. So why do we need to mimic the in vivo situation? Like in order to have a rapid testing of drugs, and also to have like we can also screen the drugs, so we can like find out which drugs can be used for better treating the device. Sorry, which drugs can be used for better treating the disease. Okay, so we need to mimic the in vivo situation of our body, and there are various structures that are indicated here. Which one do you think can mimic the in vivo situation more faithfully? Okay, let's say we are administering drugs into our body. The drugs will get absorbed in the bloodstream and it will flow. And also it will react with various cell components present in the blood. So we need something that will mimic the flow of the blood. Okay, so IDE structure we can use to characterize the electrical impedance. Other than that, it cannot do anything much. So this is wrong. Okay. And then microtubules with peristaltic pump and microfluidic chips. So these are the two options which are like feasible. So the correct answer is microfluidic chips. So before that, let us see this figure where we are having some tubes which are connected to a peristaltic pump. So this is a macro scale version. So we have a peristaltic pump and we have tubes connected to it. This tube can like at the end reach some well or reservoir where the fluid will get accumulated. The function of this peristaltic pump is to control the flow through the uh, tube. So in option C, we have microtubules with peristaltic pump. Means the tubes will be in micro scale with peristaltic pump. This kind of structure is system is feasible. However, the only thing that this kind of system can mimic is the flow of the let's say flow of the blood through the veins or something like that. It cannot mimic the temperature of the body. So when we are talking about in vivo, we want all the conditions that are present in the body to be mimicked. So one thing that is absent here is the temperature. So by using a microfluidic chip, we can more accurately uh, mimic the flow of the in vivo, the human body, and also we can have various complex microchannels which will which can be designed so that they will take into account the various effects that are related to the flow of the cells through the channel, as well as the interaction of the cells with other cells in the channel. So in the case of the peristaltic pump, we can control only the flow through the channel. We cannot also control how it will interact because we are having just a tube, right? But in this case, in microfluidic chip, we can like design certain like different kind of microfluidic channels where we can control how like if there is some particular kind of interaction happening, we can make sure that two cells are interacting at a particular point, and these kind of things we can do. So to mimic in vivo conditions of our human body more faithfully, we'll go for microfluidic chips. Okay, this is the correct answer. Now let's move on to the next question. And before we move on to the next question, I would like to add few other points. So um, the microfluidics can accurately control the fluid behavior, and also it can adjust the flow induced force so that it is relevant to what we see psychologically. And another advantage is we need a very small sample volume, and we can have a system which is having a very high throughput. So these are some of the advantages. And in this figure we can see like how the blood is flowing from the arterial blood to various organs, and like at what point it goes to the venous blood. So this is kind of the mathematical model of a human. So what we want when we want to design a in vivo system is that it should accurately or like closely model these the human system. Okay. So now let us move on to next problem, problem 3. Any doubts regarding question 2? So in problem 3, we have a question is a micro heater is fabricated on a silicon wafer followed by deposition of the insulation layer. A metal layer is deposited and it is patterned to get IDE structure. IDE is interdigitated electrode. The fabrication process of this device is a how many mask process. So option A is 1, option B is 2, option C is 3, option D it is user dependent and cannot be predicted. So what is the correct answer? Okay. So before we look into the correct answer is 3 masks process. So before we like look into that, what are the like how does the cross section of this structure, that is a micro heater that is fabricated on a silicon wafer, look like? And then we will look into what are the steps used to fabricate that kind of structure. Okay. So let us say we have a silicon substrate. So this is our silicon substrate. On top of that, we'll be having an insulating layer. So this is our insulating layer, which is silicon dioxide. Then uh, we are fabricating a micro heater on top. So that is fabricated using nichrome. So this is how my patterned micro heater will look like. Then on top of that, we are again having an insulator layer. Let's say that is oxide again. Okay. Then on top of that, we are fabricating an IDE structure. Okay, let's say this is forming some kind of planar kind of. Uh, so this IDE can be fabricated using gold. So we will not just use gold. We will use gold with addition layer of either titanium or chromium. So this is how your cross section will look like, and I'll write what are the layers. Okay, so this is gold, this is silicon dioxide, This is nichrome, which is used for making the heater. Okay. And this is silicon layer. Okay. So this is how the structure, cross section of the structure will look like. And now let us look at the process steps. So first we will start with silicon wafer. Then we will do oxidation of the silicon wafer. Right. So this is so that there will not be any short between the silicon wafer and the heater. So this is how the so next we will follow by lift off deposition of Ti gold. Sorry, lift off deposition of the heater. So here in this case, and then we again have then again in order to prevent short between the metal layer that will come above the heater, that is the IDE. We will do one more deposition. So after this, once we have done the deposition of SiO2 using PECVD, we have to pattern the SiO2. Why do we need to pattern? It is because we need to like take contacts from the electrical heater to the top. Otherwise, like we will not have any contacts from the heater, so we cannot give any voltage to the heater. So we'll have to pattern SiO2 layer. So let's say this is our electrical contact. Then how our SiO2 will get patterned is like this. Okay. This is our pad for the heater. So ideally we'll have two contacts. So here I'm just showing only one. Then we will go ahead with lift off deposition of the IDT, interdigitated electrodes. Okay. Okay. So here now like we need a mask every time we need to pattern the layer. Okay, if you look at how many times we have to pattern the layer, then we can see that while doing lift off we need to have a pattern, right? So here we need mask 1. Then we are patterning SiO2 to form contact. So here we need mask 2. In this case we are doing lift off, and in this case we will be doing etching. Because if you are using PECVD, the deposition usually happens at temperatures of 200 to 300 degrees. So at that temperature, the photoresist will not be able to sustain. So we will not be using like photoresist, like we will not deposit SiO2 using photoresist as a mask or something. We'll have to do blanket deposition. Then we'll have to follow this by etching. Then while depositing the ID electrodes, we will need another mask. So here we need 3 masks for this process. Thus the correct answer for this question is, as we see here, the fabrication process of this device is a 3-mask process. Is this clear? If it's clear, we can move on to the next question. Okay. So now let us see problem 4. Static platform for determining efficacy of a drug gives results different from that of dynamic system. So this we saw in the one of the lectures. The reason behind it is option A, drugs cannot be properly placed on the tissue in static system. Option B, human body is a dynamic system, so it cannot be replicated properly using static system. Option C, human body acts as a static system, so statement is false. Option D, human body may be a dynamic system, but static replication gives the same result as a dynamic system. So which is the correct answer for this question? Okay, we know that human body is a dynamic system, right? So drugs can, the first answer is wrong because we can have different kind of channels or tubes that will make sure that we can flow the drug properly on the tissue in the static system. So this is wrong. Human body is not a static system. So this is also wrong. A human body may be a dynamic system, so but static replication gives the same result as dynamic system. So that is wrong because in one of the results we saw that we were getting different results when we were using a static system in order to uh, a static system compared to that of a dynamic system. So this is wrong. The correct answer is option B. Human body is a dynamic system, so it cannot be replicated properly using static system. So in human body, it is dynamic because blood is continuously flowing through, and various cells will interact with each other continuously. So there is not just one like for whatever reaction that is happening, there is not just one factor which is sole responsible. Like sometimes it's a combination of factors that we have to take into account. Okay, so and this figure we saw earlier, right? So here the blood will flow through various organs. However, there will be some interaction between them as well. So in order to model this accurately, we use a microfluidic channel so that we'll be able to study the various interactions. And then let's say when we inject a drug in a human body, depending on the concentration of the drug as well as the time for which the drug is injected, there will be some varying response. So the drug metabolism changes with time. Also, the concentration will also change with time. So we can say that since this is changing with time, we can actually say it is a dynamic system. So in order to study, so this happens in a human body. So in order to study this dynamic system, we need to have a model which is also dynamic in nature. Then only we'll be able to kind of closely study the human body system. So is this clear? So, that's why human body is a dynamic system and it cannot be replicated properly using static system. Now let us move on to next problem, problem 5. With regards to the microfluidic chip for rapid drug screening that was discussed, evaluate whether the following statement is true or false. The normalized impedance of the drug susceptible cancer cells increased upon addition of the drug. Option A is true or option B is false. So, in the microfluidic chip for rapid drug screening, what we are testing is we are testing the normalized impedance of the cells. So, we will study how the impedance is varying when the drug is added and without addition of the drug, how the impedance is. Hmm. Here it is asked whether the impedance increased on the addition of the drug or not. So is this true or false and why? Okay. So here we see something called normalized impedance, right? So normalized impedance is generally given by this formula. So this is the equation 1. ZM is the impedance of the culture medium where there is no cells, and Z cell is culture medium with cells. So generally, in order to find the impedance or do any kind of testing, we suspend we suspend the cells in culture medium. This culture medium or any other medium will be chosen so that it will kind of replicate the whatever fluid we are studying. Okay. And here you can see the Uh, yes. So that is a normalized impedance. Um So, does the normalized impedance increase, or does it decrease on the addition of the drug? What happens when we are, so another important point that we noted is drug susceptible, which means that these cancer cells will like die because of the drug. So when the drug is administered into the system, the drug can kill these cancer cells. So, this means that there is some kind of change that is happening in the cancer cell due to the when we are giving the drug to the system. So, whether the impedance will increase or whether it will decrease. So here we can see that this is the cell count and versus time for drug tolerant cells and drug susceptible. Tolerant means they do not have any effect to the drug. Means even if you are giving the drug, it will not affect the cells much. And susceptible means like giving the drug will affect the cells. So here you can see that the cell count percentage for the drug susceptible cells is lesser, right? So, as we are giving the drug will kill the cancer cells. So, the concentration of the cancer cells will decrease. That is what is happening in the system. How this will affect the impedance of the system? Okay. So, like each cell will have some amount of impedance due to like it having some amount of conductivity, and let's say if a cell is undergoing death due to the drug that is administered to it, the impedance value will decrease. Why? This is because the cell membrane is compromised, and like then as the cell membrane is compromised, whatever the contents that are inside the cell will start flowing out. So we know that the cancer cell, which is will have lower impedance. Okay. And so here this count is the number of live cells. So like we can say that the electrical impedance will decrease with time rather than increasing with time. Okay. So this is wrong. Decreased. This is decreases with time. So we can say that the overall impedance of this cancer cell will decrease with time rather than increase with time. Okay. So this is wrong. And another thing that is to be noted here is that here it is mentioned upon addition of the drug. Okay, so drugs will take certain amount of time to get to react with the cancer cells in order to kill the cancer cells. So just immediately on the addition of the drug, we will not have the cancer cells dying. So it will take some amount of time. Okay. So here in this figure, we can see the cell percentage cell count of drug tolerant cells as well as drug susceptible cells. With as time passes, like for drug susceptible cells, we could see a very steep decrease in the cell count. That is because the drug will kill the cancer cells. So and the impedance of a cancer cell, dead cancer cell, will decrease. And the reason behind it is that the cell membrane it gets ruptured because uh, it is compromised by the reaction with the drug. So the whatever contents that are present inside the cell will flow out of the ruptured cell membrane. This will cause a low impedance in the uh, cells that are dead. Okay. So like here we can see that so in this statement what all is wrong is that instead of so the impedance, normalized impedance will decrease And another thing is immediate. This reaction does not happen immediately on the addition of the drug. It will take some time for the drug to get absorbed by the system and like react with the cancer cells. So immediately upon addition, we will not be seeing any change in the impedance. After some time, we'll be seeing some change in the impedance. So this we can see here also. At time t equal to 0, we do not see like much change, but as the time increases, we are seeing change. So it will take some time for the drug to react with the cancer cells. So to summarize question again, um, problem 5, we have the question: the normalized impedance of the drug susceptible cancer cells increased upon addition of the drug. So this statement is false. And what corrections we can make regarding to the statement is that the impedance actually decreases, and like so this one is also wrong upon addition of the drug. So it takes some time for this change in impedance to happen. Okay, is this clear? If it's clear, we can move on to the next question. Problem 6. Consider the following statements related to the microfluidic chip for rapid drug screening that was discussed. The so We have some options. You just have to tell which are the correct ones. Okay, option A is the substrate used was a silicon wafer. Option B, the electrical sensor interdigitated electrodes were patterned directly on top of the nichrome microheater. Option C, both. D, neither. So which one is the correct answer for this question? Okay, so this is the microchip that was discussed for rapid drug screening in the lecture. So here you can see the actual fabricated device. And if we draw the cross section of this kind of, what we have is we have a glass substrate. Then on top of the glass substrate, we'll have the microheater, the patterned microheater. Then on top of that, we will have some insulator in some regions. So these two will form the contact paths for the microheater. So this is insulator. This is nichrome. Then on top of that, we have IDE structure. Then again on top, we'll have the micro channel, which is made by using the PDMS structure. Okay. So from this, what on all we can say is that in option A, it was mentioned that the substrate is silicon, right? So here we can see that the substrate is not silicon, it is glass. Okay. So option A is wrong. This was glass. And in option B, it is mentioned that the electrical sensor interdigitated electrodes were patterned directly on top of the nichrome microheater. And in previous classes, we have already discussed that we do not do this because we don't want electrical short between the microheater and the electrode. So we'll have some insulating layer between them. So this is also wrong. So the correct answer is neither. This is the correct answer, neither. Now let us move on to the next question, problem 7. For fabrication of SU8 pillars, which one is the standard process flow? Option A, photoresist coating, soft bake at 363 Kelvin. So 363 Kelvin is, you have to subtract 273 Kelvin from it, right? So you'll get 90 degrees centigrade. UV exposure, development, hard bake at 393 Kelvin. So 393 Kelvin is 120 Kelvin, 120 degrees centigrade. Option B is photoresist coating, soft bake at 338 Kelvin. So think 338 Kelvin should be around 338 Kelvin is at 65 degrees centigrade. Then it is followed by UV exposure development hard bake at 368 Kelvin. So 368 is 95 degrees centigrade. Option C is photoresist coating soft bake at 338 Kelvin. UV exposure hard bake at 368 Kelvin and development. Option D is photoresist coating soft bake at 363 Kelvin. UV exposure hard bake at 393 Kelvin and development. So which one is the correct answer? And before that, SU8, you know that SU8 is a negative photoresist. So the sequence of steps that we use in a negative photoresist are somewhat different from that of the positive photoresist. Another thing is that in negative photoresist, the regions where the exposed regions will remain insoluble, whereas the unexposed regions will be soluble. So which one is the correct process flow? The correct answer is option C. So I'll tell why. So these are the steps that are involved in like when you are using SU8 as a photoresist to pattern. So first is substrate pre-treatment. So here what we will do is we'll clean the wafer. So either using Piranha or we can do solvent cleaning, which involves acetone clean followed by IPA, then DI water. Then we will coat SU8. This is also after cleaning with DI water, we will do dehydration to remove any moisture that is present on the substrate. Then we will follow this by SU8 coating. So here we will just dispense SU8 on the substrate. The substrate will be mounted to some vacuum chuck. Then appropriate rotation as well as rotation duration as well as acceleration will be input into the system. So depending on the rotation speed as well as the time for which the rotation happens, the thickness of the photoresist will vary. This will be seen in the data sheet. So once the spin coating is done, this is followed by soft baking. So in soft baking, we'll try to solidify the photoresist by removing some of the solvent that is present in it. Then after soft baking, we will follow it by SU8 exposure. So here the exposed, since it is a negative photoresist, exposed region will remain insoluble, whereas the unexposed region will get dissolved later when we are doing the development. So after exposure, we follow it by post-exposure baking. So during this post-exposure baking, what happens is that like the exposed regions will become cross-linked. So like it will become more like hard to remove. This is then followed by SU8 development. So whichever regions are uh, whichever regions are not cross-linked, they will get dissolved in the developer. This is then followed by rinse. Rinse means we will rinse with DI water and then we will dry the sample using nitrogen gun. So if we want to use this as a mask for etching or as a like a hard mold kind of structure, then we'll go for hard baking, and this is optional. So there is also another step that we use after coating. So that is called as edge bead removal. So what happens is that when we are coating, since it is based on that centrifugal force, like the thickness will vary from the center to the outside, and at the outside the thickness will be very high. So we'll have something called edge bead. Means the thickness will be very much high at the edge, so forming some bead kind of structure. To remove that, we will just dispense acetone at the edge of the wafer while it is rotating, not to remove the edge bead. So here in this figure they are removing around 5 mm, but again depending on your sample size, how much you remove will vary. So these are the steps. Now let us go back to the options that we are having. So in option A, after UV exposure, we are doing development and hard bake, so that is wrong. Okay. So option A and B are wrong. Then in option C, what we are seeing here is we have the same steps, but the thing is the temperature is different. So in the case of SU8, the soft bake temperature is 65 degree and the hard bake temperature is 95 degree. So we do not do it at very high temperature of 90 degree and 128 degree. Okay, so this is wrong. The correct answer is option C. Okay, so for fabrication of SU8 pillars, which one is the standard process flow? Option C is the correct one. So now let us move on to the next problem. Problem 8. In fabrication of microfluidic devices, PDMS can be used. So PDMS belongs to this group of materials commonly referred to as silicone. Generally, PDMS is patterned by which lithography technique? Option A, optical lithography. Option B, E-beam lithography. Option C, soft lithography. Option D, all of these. So these are various lithography techniques, and PDMS is commonly used for microfluidic devices, that also you know. What kind of lithography are we using to pattern? I think we had this question in one of the earlier discussion sessions as well. The correct answer is soft lithography. Okay. So soft lithography, like it is a family of techniques where we fabricate structures or we try to replicate structures using some kind of mold or stamp. So this is used to like make or we can also use conformable photo mask. So this will act as a mold for our elastomer like PDMS. Okay, and it is this type of lithography is called as soft lithography because we are using it to pattern soft materials like elastomeric materials like PDMS. So these are the various steps that are used in fabrication of structure using PDMS. So uh, here you can see that first we have to make the master mold, means the mold structure. So here in this figure, they are using a silicon wafer. This is then coated with photoresist. This photoresist is optical photoresist. Then what we are doing is we are adding a mask. Then we'll expose the pattern. So here, depending on whether the pattern is having uh, in this case, we can say that this is a negative photoresist from the structure. So, whichever region, so the first step in this is like having making a master mold. So we take a silicon wafer, then we deposit photoresist on it. Then we will have a mask, like having a particular pattern, and then we will have a UV light exposure. Then we will put this substrate in a developer. So what will happen is the photoresist will get dissolved, and after etching the substrate, we are left with this kind of pattern. So that means that the exposed region remains, whereas the unexposed region is removed. So we can say we are using some negative photoresist for this kind of pattern. So this is our master mold. Then what we'll do is we will pour on PDMS. We will cure PDMS at 65 degrees centigrade, and then we will peel away the PDMS. Then we are left with some embossed microstructures. So this will be like converse kind of pattern. So what if we are looking at the cross section, what we will have is we'll have some kind of thing like this. So this is how your PDMS will look like. So PDMS is dimethyl siloxane. And one advantage of this soft lithography is that we can make multiple replicas of this same using one master. We can make multiple replicas. So this type of soft lithography is also called as replica modeling. So there are other types of soft lithography as well. Okay. And also the time that is taken for completing this entire process is short, like compared to doing other forms of lithography, etching and so on. Then if you look at other options, optical lithography, we use the visible light spectrum in order to expose, not the visible light spectrum, we use optical wavelength in order to expose the photoresist, and in E-beam we use electron beams to expose the photoresist. So soft lithography is generally used for elastomeric materials. Is this clear? Now let us move on to the next problem. Problem 9. In the microfluidic chip for rapid antibiotic susceptibility testing that you have seen in the lectures, the antibody was used for what purposes? Option A, to capture the antibiotics when they are introduced. Option B, to capture the bacteria from the sample. Option C, to ensure better bacterial growth during incubation after adding antibiotic drug. Option D, to enhance the killing of the bacteria by the drug. So in here, we are having a microfluidic chip that is for testing the antibiotic susceptibility, and we are using antibody in that chip. So why are we using that? Okay, what are antibodies? So antibodies are generally produced by the immune system of the body in order to like in response to exposure to bacteria, fungi or viruses. So these will get attached to some antigens or markers on the bacteria, and that will help the body fight the bacteria. So if the when the antibody gets attached to some kind of marker on the bacteria, the immune system will be easily able to identify that and it will destroy the bacteria. Okay, so here this is what antibody, like the function of antibody in a human system. So by using the same like mechanism, we are using antibody to capture the bacteria from the sample. This is because the antibody will get bind to the antigens in the bacteria. So these antigens will be present on the surface of the bacteria or in the outer membrane of the bacteria, and thereby we can like use, and each another important thing is antibody will recognize only one specific antigen. So depending on the nature of the antigen, antibody will like it will just get bind to one type of bacteria. However, in certain cases, it may like bind to the wrong antigen as well. But in that case, we'll get some false positive results. So the answer for this question is option B, to capture the bacteria from the sample. So here we are using the same like in our body, antibody gets it gets binded to the antigens in the bacteria, thereby helping our immune response to attack that particular bacteria. So we are using that like we are trying to mimic that, not mimic that, we are trying to use this kind of mechanism in order to capture the bacteria from the sample. So one advantage of this is that like when we are taking a sample, it will contain many other cells in addition to bacteria, it may contain other pathogens as well. When we are testing for antibiotics, like if we are having only that particular bacteria, then you can say like you will have a better like you can say that this particular antibiotic is susceptible to a particular bacteria, means it can be used to treat a particular bacteria and so on. So here you can see this is another application where they are having a functionalized electrode with antibody, and when they have a sample which is having bacteria cells, it will get adsorbed, the bacteria cells will get specifically adsorbed to the electrodes. This is because the antibody will get bound to the antigens on the bacteria surface. If we are not, let's say in your microfluidic chip, if you are not using an antibody, what will happen is like there will be a lot of other cells in addition to the bacteria as well. So this is the figure of a microfluidic channel where they are having antibody along the microchannel. So like say this target cells are our bacteria cells, like they will kind of get added to the antibody. So uh, this is the microchip that was discussed in the lecture. Okay. Now let us move on to problem number 10. The following statement is related to the experimental results that were discussed for the antibiotic susceptibility testing microfluidic chip. Upon addition of the antibiotic drug to the microfluidic chip containing the captured bacteria, the normalized impedance decreased. So already we saw the normalized what the definition for the normalized impedance. Is this above statement true or false? Option A is true, option B is false. Okay. So the antibiotic susceptibility testing microfluidic chip. So it is generally used to determine whether a bacterial pathogen is sensitive to a particular antibiotic, or we can also test multiple antibiotics by having multiple channels. So in this testing, like when we are using a microfluidic chip, we will test the electrical impedance of the channel. Okay. So here, here again, upon addition of the antibiotic drug to the microfluidic chip containing the captured bacteria, the normalized impedance decreased. Is it true or false? Okay. So the correct answer for this is false. Let's see. Let us see why. Okay. So what happens when antibiotic drug is given to a bacteria? It will kill the so it is again. It depends on whether the bacteria is affected by the antibiotic drug or not. Uh, so when the antibiotic concentration is increased, the amount of bacteria that is present in the cell culture will start to decrease because the bacteria will start to die. So there will be less charge in the sample solution, and this will cause some change in the normalized impedance. So as the bacteria cells die, the impedance will decrease. However, there is another thing is upon addition of the antibiotic drug, that is what is mentioned. So for an antibiotic to eradicate a like bacteria, so three types of main things should happen. First is it should bind to the target site in the bacteria. Okay. So it has to reach to that particular site. So it will take some time to reach. It has to penetrate through various the outer organism. Let's say if your bacteria is present in your lungs, then it has to penetrate through the organ. Then it also should be avoided being pumped out of the membrane, and In this process, while it tries to reach the target site, it should remain intact as a molecule. And another thing is, once this antibiotic drug reaches the target site, if your binding site has changed its molecular configuration, then also the drug will not be able to, sorry, the antibiotic drug will not be able to bind to the binding site. Uh, so that is another thing. Then after it is attached to the binding target, it should not only just one target, it should get attached, it should get attached to multiple binding sites. So multiple, like if there'll be multiple bacteria, so it should get attached to multiple bacteria as well. Then only the concentration will decrease. The concentration of the bacteria will decrease, and the concentration of the antibiotic in the organism will increase. Then it also should remain in the binding site for a sufficient amount of time for the metabolic process of the bacteria to diminish. So if the metabolic process of the bacteria is sufficiently diminished, then the bacteria can be killed. So for this all steps to happen, it needs a sufficient amount of time. So the reaction does not happen just immediately on the addition of the antibiotic drug. So the above statement is false. The main reason is it's mentioned upon addition of the antibiotic drug. So it will take some time for the antibiotic drug to react with the bacteria in order to like see whether the impedance is changing or not. Okay. Okay, so these are the three main steps, like how antibiotic reacts with bacteria. So this is what happens when like in our human body. So since we are trying to simulate in vivo conditions in microfluidic chip, we will also like take into account the amount of time it should take to like reach from the site where the medicine is injected to the target organism. So that's why the statement is false, because immediately on the addition of the antibiotic drug, we will not see a response. Is this clear? If this is clear, we can move on to the next problem, problem 11. Okay. We can measure the impedance of any tissue by placing it on interdigitated electrodes. We now apply a drug to this tissue. If this drug is effective in killing the tissue, then the impedance option A increases, B decreases, C remains the same, D none of the above. So which is the correct answer? I think we saw this question in this content has been kind of repetitive, like similar. The concept has been repetitive. So what is the correct answer? Okay. So the correct answer is option B, decreases. So we know if the drug is killing the tissue, then what it will do is it will affect the cell membrane, like membrane of the tissue. So since the membrane of the tissue gets degraded, then the impedance will start to decrease. This is because the conductivity will increase for the particular tissue. And this impedance is called as, like, we can say it as bioimpedance. It is the ability of the biological tissue to oppose the electrical current. Yeah, and it is represented by Z. Z is voltage divided by current. Okay. So next is problem 12. What is the soft bake condition of SU 8? So this I think we saw in a previous question. Option A is 90 degrees centigrade for 1 minute. Option B is uh, Option B is 90 degrees centigrade per time, depends on the thickness of the resist. Option C is 65 degrees centigrade per 1 minute. Option D is 65 degrees centigrade per time, that will depend on the thickness of the resist. So which is the correct answer? So here what we are asking is soft bake condition for SU 8. Okay. So SU 8 is a negative photoresist, or like we can say it is a negative resist, and so there are like various types of SU 8 resist. Depending on the viscosity, they have various like product lines. So one of them is SU 8. In SU 8, by varying the SU 8 10, by varying the spin speed, you can coat between 10 to 25 micrometer. Again, since the thickness of the resist is varying, like the amount of solvent that is present in the entire resist will also be different, right? So, like we know the soft bake temperature is 65 degree. We cannot soft bake at the same time for different resist, with a resist which is having different thickness, because it will not evaporate the considerable amount of solvent. Okay, so the correct answer is option D, 65 degrees centigrade, and the time will depend on the thickness of the photoresist. So here this is from a data sheet of SU8 photoresist, and here like is the soft bake process that they have mentioned in their, for their particular product. They tell that it has to be baked at 65 degree centigrade, and the time will vary depending on the thickness of the resist. So this is then again followed by baking at 95 degrees centigrade. This is for this particular product. Again, for a different company and different line, the specs will vary. And here you can see that there are various like types of SU8 resist. So SU8 2, SU8 5, 10, 25, and so on. So the thickness, and here you can see the thickness of the photoresist. So the thickness is varying. And one important thing that you can see is that as the thickness of your resist is increasing, the time for which you are doing soft bake is also increasing. Okay. So like the correct answer is options D, and it is, we are soft baking at 65 degrees centigrade, and the time will depend on the thickness of the resist. So this so now let us move on to problem 12. While using SU8 as a resist of the lithography, post exposure bake is done at 95 degrees centigrade after PR development. Is this true or false? Okay. So we already saw the steps, right? So we have for SU8 lithography, we have post-exposure bake, we also have hard bake, we also have a soft bake. So is it done after the PR development, or in what sequence does it come? Okay, the correct answer is false. So here if we see the sequence of steps that are required for making patterns using SU8 photoresist, which is a negative photoresist, the post-exposure bake comes before the SU8 development. Okay. So it does not come after the PR development, it is before the PR development. So the correct answer for this question is false. Option B. Now let us move on to problem 14. The hole for the inlet and outlet of the microfluidic chip is created on PDMS by option A, soft lithography, B, photolithography, C, accupunch with fine needle, D, screen printing. Okay. So which is the correct one? Correct answer for this question. We have to make holes for the inlet and outlet for the microfluidic chip. Okay, to make like holes, we need to uh, have a either sharp structure. So like soft lithography is used to pattern the microfluidic channel. So that is not correct, and it's not photolithography as well. Printing is generally used to deposit or a patterned material. So a material with some particular kind of pattern. So that is not correct. Occupants with fine needle. So like if you want to make a hole, we need to pierce the chip using something sharp like a needle. And since it is PDMS, like we can use some needle to make holes. Right? So acupuncture with fine needle is the correct answer. PDMS is an elastomer, so it is easy to use a needle to make this kind of outlet and inlet. Okay. Next, let us look at problem 15. The PDMS mold is attached to patterned glass substrate to form microfluidic channel by option A, heating, B, oxygen plasma, C, nitrogen plasma, D, argon plasma. So what we have is like if you are having a micro channel using PDMS mold, then we'll have something like this. And like if you want to make a enclosed channel, we need to attach something at the bottom. So here we are using a glass substrate, and this is PDMS. So this is the like channel cross section of the channel that we are seeing. So how we are attaching this mold to the glass substrate? The options are A, heating, B, oxygen plasma, C, nitrogen plasma, and D, argon plasma. Okay, so the correct answer is option B, oxygen plasma. So what happens is that like these are the steps in a microfluidic device fabrication. So at the top we have PDMS where we have formed a microfluidic channel, and at the bottom we have glass. Okay, so the surface of PDMS will have SiO bond, and the surface of glass will also have SiO bond. Okay, because it is silicon dioxide, SiO2. So once we pattern a PDMS substrate by using the replica modeling, then we will oxidize this PDMS in air or oxygen plasma. So this will remove any organic or hydrocarbon material that is present on the surface of this PDMS. And what will happen is we will be having SiOH bonds at the surface. So similarly, when we do oxygen plasma treatment of glass, it will also remove any so it will result in the formation of SiOH bonds on groups on the surface. So this SiOH is called as silanol groups. And one important property of this kind of group is that it is more hydrophilic. Hydrophilic means it is water loving, and that means it will easily like anything that is having water will get easily wet on the substrate. Wet means it will easily spread on the substrate. After oxygen plasma activation, when we keep this PDMS in contact with the glass substrate, what will happen is we will have the formation of SiO bond. So this is siloxane bond. This is very strong, and this will create an irreversible seal. Okay. So by doing this, we can form micro channels structures. So not just like we can bond PDMS with glass substrate, we can also bond PDMS like which is treated with oxygen plasma with another PDMS which is treated with oxygen plasma as well. Okay. So uh, the correct answer for problem 15, the PDMS mold is attached to a patterned glass substrate to form microfluidic channel by using oxygen plasma. Okay. Now let us move on to problem 16. In problem 16, the microfluidic chip for rapid bacterial antibiotic susceptibility testing discussed in class was made on option A, glass substrate, B, silicon substrate, C, plastic OHP sheet, D, silicon carbide substrate. So this is for rapid bacterial antibiotic susceptibility testing. So this is a direct question. The correct answer is option C, plastic OHP sheet. Okay, OHP sheet is just a overhead projector sheet. It is a transparent sheet which is used in that projectors, and it is also flexible. So generally, for like testing of these chips, we need some kind of substrate material that is relatively cheap. Right. So we are using a plastic OHP sheet in this case. So now let us move on to next question. Question number 17. In vitro experiments, matrigel is used to mimic the dash like in our body. Option A, tissues. B, tumors. C, extracellular matrix. D, blood or media. So I think in one of the like content where we are taking the tumor cells from our body, then we'll put them in kind of a medium. So in that, matrigel will act as a medium. So like what it is actually mimicking our human body. Why do we need to keep it in matrigel? Why can't we keep it in some kind of other cell culture medium? Okay. So matrigel is generally used in many like bio applications, and it is used for cell culture and tissue engineering. It will like because it will provide some good environment for growth of a cell as well as for differentiation. Again, this matrigel is extracted from I think tumor cells of mouse, a particular tumor cell. So like this you can see oh, sorry. The matrigel is generally extracted from tumors of a mouse cell. Matrigel is extracted from tumor cells of a mouse. So in that also, like it is a part of something called as extracellular matrix. Okay. So the correct answer for this question, the in vitro experiments, matrigel is used to mimic the extracellular matrix in our body. So let me tell you what it is. What is an extracellular matrix? Here you can see some cross section of cells. So here you have epithelial cells, and then you have something called as basement membrane, interstitial matrix, then again blood vessel. So the extracellular matrix is a combination of basement membrane and the interstitial matrix. It will have like it is consisting of lot of proteins and other molecules that will support and will give some sort of structure to the cells or tissues in our body. So it will also interact with nearby cells and plays a very important role in cell growth, cell movement, and other functions. This extracellular matrix is generally present in normal cells as well. However, if we consider the cancer cells, okay, they will interact with their extracellular matrix at each step of the metastatic process. And like from their interaction, we can tell how the cancer will progress. So from like if you are looking at the extracellular matrix of a normal tissue, and if you are comparing that with that of a cancerous tissue, then it will be looking very different. Okay. So like when we are studying cancer cells, we want to like it will be anyway present surrounded by the extracellular matrix. So we want to keep the cancer cells in the extracellular matrix so that we can mimic. So in matrigel, we want to keep the cancer cells in matrigel, which is also extracellular matrix, but it is from rat, like tumor cells of rats, so that we can mimic the actual extracellular matrix in our body. Okay, so to summarize, cancer cells are kept in matrigel so that we can mimic the interaction of the cancer cells with the extracellular matrix that is present in our body. Okay, okay. So now let us move on to problem 18. What is the method used to make heater or IDE pattern on plastic substrate? Option A, soft lithography. B. Photolithography. C. Direct writing using UV laser. D. Screen printing. So here we are using plastic substrate, meaning like it cannot withstand high temperatures. So the temperature up to which we can go for this plastic substrate is less. Okay. So these are the options. Which one is the correct answer? So here we know soft lithography is generally used for patterning PDMS, right? We cannot use to make a heater or IDE pattern. Photolithography we can use, but the thing is the metal deposition temperatures can be high, so we cannot use a plastic substrate in that case. Direct writing using UV laser is also wrong. The correct answer is screen printing. Okay, so this is how like screen printing will look like. So first, let us take a substrate. Can be any substrate. Uh, we will have some kind of mesh screen. So that is on top of a photo emulsion mask. So here, how our photo emulsion mask will look like is like this. This is for a ID pattern. Okay, but for our so this is from a reference from a paper. But for our question, we'll be having like as per our question, we'll be having a heater pattern. The pattern will be just different. That's all. Okay. So this is our photo emulsion mask. So here what happens is this region is transparent. Not transparent means it's uh, like a through hole. It's like it is etched through. Okay. The unshaded region is etched through. The shaded region is having solid material. That's how it looks like. Mhm. So what we'll do is we'll keep a mesh kind of screen on top of this, and then we will use this is called as squeeze squeeze. So that is used to we will pour some paste on that mesh screen which is on top of this photo emulsion mask. Then we'll use the squeeze to distribute the paste in order to along the like entire mask. You would have seen screen printing for clothes, right? So it's just the same process, but we are doing it in micro, like smaller scale. That's all. And at the end, we will come with this kind of pattern. So if you're having this region is like see-through region, okay, means it's etched region. Huh. So it's like having a stencil, stencil, right? And then you are just placing a mesh screen on top of the stencil. Then you will just like use a squeeze or something to distribute the ink across the stencil. So when you remove your stencil, you will see that whichever regions are having like whichever regions are kind of etched out in your stencil, in those regions you will see the corresponding pattern. That is what is happening here in this figure. Okay. So screen printing is generally used because it is a very attractive fabrication technique because due to it's very simple, affordable, and it has a high scalable potential. Means you can use the same mask to make multiple structures. Again, the resolution of the screen printing technique may be like somewhat higher than that of the uh, conventional optical lithography or photolithography or soft lithography processes. Higher means like if you can make nanometers scale features in your e-beam lithography, you can make maybe like somewhat larger structures using this. Like you cannot make nanometer scale structures using screen printing. However, maybe you can make millimeter size structures or centimeter size structures using screen printing. Okay. So next we'll move on to problem number 19. How is a microfluidic chip for drug screening functionality different from a microfluidic chip for antibiotic susceptibility testing? So these are the two types of chips that we saw in our lecture. So how is it both different? So now let us see. In the first figure, we are having the microfluidic chip for drug screening. And in the second one, we are seeing the figure of the chip that is used for antibiotic susceptibility testing. Okay. So in both the cases, we can see that there are, like in the first case for drug screening, we are seeing that there are many multiple channels, whereas in the case of antibiotic susceptibility testing, there is only one single channel. So both have heaters and both also have ID interdigitated electrodes along with contact pads for measuring the impedance. Okay. So another important difference between the two, apart from having different number of channels, is that in the antibiotic susceptibility testing, we'll have some region where like the channel will be coated with antibodies, so that these antibodies will get adhered to bacteria, a particular bacteria, so that we can test that particular bacterial cells for antibiotic susceptibility. In the case of drug screening functionality for like general cancer cells, we do not need to have any specialized material adhering the surface. Like we don't need to have any antibodies which are coating the uh, microfluidic channels or so on. Okay. So now let us move on to next problem. Problem number 20. The heater is required in the microfluidic chip for rapid drug screening. Option A, to keep the cell alive by giving 37 degrees centigrade. Option B, to improve the sensitivity of IDE sensing. Option C, to kill the cells by providing 37 degrees centigrade. Option D, both A and B. Okay. So what is the correct answer for this question? The correct answer for this question is option A, to keep the cell alive by giving 37 degrees centigrade. So 37 degrees centigrade is the human body temperature. Okay, so we already saw that we are using heaters to increase the temperature, but like say heaters will just keep on increasing the temperature, right? So how do we maintain the temperature? We will maintain the temperature by having some kind of feedback system that will means we'll heat the chip, and also we will do cooling of the chip so that we will maintain the particular temperature, which is around 37 degrees centigrade. Okay. So there will be some kind of feedback system which is connected to the heater. So it will provide the heater with some adequate amount of voltage or current. It will provide the heater with adequate amount of current so that it can control the rate at which the temperature is increasing. So once initially the rate at which the temperature is increasing will be high. Once it reaches 37 degrees centigrade, the feedback system will kind of take care the current flowing through the heater. So it will reduce the amount of current that is flowing through the heater. By thus, this will maintain the system at constant temperature around 37 degrees centigrade. And we need this temperature because it is human body temperature, and when we are using the microfluidic chip for rapid drug screening, we want to closely simulate the human body conditions, and that is why we need a heater. Okay. So any other questions? If not, we can end this live session. Thank you.